Welcome to Module 7, a mini lecture on hypothesis testing and two-sample designs. At the end of this module, you should be able to identify whether design includes independent samples or paired samples. There's going to be a mini lecture going over some examples with that. You should be able to understand the meaning of significant results in a statistical context, understand the rationale for non-parametric two-sample designs versus parametric two-sample designs, and also carry out and interpret hypothesis testing output for two-sample designs. So when we have a question, there are different experimental approaches that we can take when we have two different treatments that we're looking at in terms of our independent variable. For an example that we're going to work through in this mini lecture, we're going to be looking at a study of dialysis patient education. So the question that this study is looking at is, does a programmed educational package on kidney function and renal failure improve dialysis patient knowledge? And then we have to think about how we would design this type of a study. And there are two different approaches that we could take. The first option is to take a group of people, so in this case 20 people, and randomly assign them to one of two groups, and we'll have 10 people in each group. So group 1 is getting no programmed educational package, and we'll look at their knowledge, and group 2 is going to receive this programmed educational package. And then what we're going to do with these two different groups is assess the knowledge of the individuals in each group using the same test in order to answer our question. And this type of a design, where we're just taking a group of people and assigning some of them to one treatment and some of them to another treatment, is a two-sample design, and therefore we would use what's called a two-sample t-test. We have independent samples here. And we use this when we have two treatments on independent samples. So if we have two different treatments, like we have here, or we have two different groups that we want to compare. So often when we think of treatments, we might think of using a drug versus a control group that's only receiving a placebo, or maybe if we have two different groups, we have groups in the Midwest and groups in California, for instance. And when we're doing a two-sample t-test, we are interested in comparing the mean responses from these two sampled groups. So the population mean of population 1 and the population mean from population 2. And our null hypothesis is that these means are equal, and our alternative hypothesis is that they are not equal. And the test statistic is for t, where on the numerator we have the difference between our means of our treatment groups. So we're using x bar because now we have sample means. And on the bottom, it's the standard error of a difference. On the left-hand equation, this is how you'll see it in your textbook, and on the right-hand side, I've actually used the sample standard deviation and our sample sizes. If you do it on the right-hand side, you can just sort of plug in those numbers. So this is our typical two-sample t-test when we have equal samples. And we have to have some general assumptions when we're using this type of a t-test, and including that our data are independent samples from the populations, so often random samples, that our data are normally distributed, that makes this a parametric t-test, and that the variance of the data from the groups are equal. So for this example two-sample t-test, when we have our question of does a programmed educational package on kidney function and renal failure improve dialysis patient knowledge, our null hypothesis is that the mean response from the population where there's no educational package will be the same as the mean response of people who are receiving, so that there's no effect at all of this education on their mean response rate from the test that they're doing, so on their mean score. And our alternative hypothesis is that there's a difference in the mean scores on the test from people who did not receive the education package and people that did. So keep in mind here that our independent variable is the education program, so whether or not they received it, and then the dependent variable is what we are actually measuring, which is the score on the test. So here we have our null hypotheses that we just talked about. Our second step, of course, is setting our decision rule, which is setting our alpha at 0.05, so that's standard. The third step is to calculate our test statistic. So we have to actually go and collect data. You know how to calculate means and standard deviations already. So here's our data. We have 10 individuals that were assigned to the no education group and 10 individuals who did receive the education. There are the means for the two groups and the standard deviations for the samples. Now we need to plug that into our calculation for t. So when we do this, remember on the numerator, that's where we have the difference between our treatments and then in the denominator, that's where we have information on the variability. So for our no education group, I'm assigning that to 1 over here. So it's going to be 14.1 squared divided by our sample size. And then for our second group, it's 15.2 squared, then divided by our number of samples that are in that group. So our numerator ends up being negative 9.9. So individuals are doing better after receiving the education than they were prior. That's why we have a negative sign. Ultimately, we're doing a two-sided test, a two-tailed test, so the negative won't really matter. And then in our denominator, we're going to have 19.881 for this part here, plus 23.104. That's for this part here. Remember, square it first, then divide by 10. That's important. Which then leads to negative 9.9 divided by the square root of 42.985, which is equal to negative 1.510. Okay, so this is our value of our t statistic that we've calculated. And then, of course, our fourth step is to compare our test statistic with our decision rule and then draw conclusions about our null hypothesis. So for that, we need our degrees of freedom, because we're going to have to look that up in a t-table. And here our degrees of freedom are based on our sample sizes for our first group, which is no education, our second group, which is education, and then we have to subtract 2. And we lose 2 degrees of freedom because for each of these, we had to calculate a population mean. We had to estimate that. And because we had to estimate that from our sample, we lose 1 degree of freedom for each one. So that's why it's n1 plus n2 minus 2, because we had to estimate 2 means based on samples. Our alpha value is 0.05, and our degrees of freedom are going to be 10 plus 10 minus 2, which is equal to 18. So when we look at our t-table, we're going to be looking at our alpha for a two-tailed test of 0.05, and we need to look at 18 degrees of freedom. So that's 2.101 is our degrees of freedom for this test. So our t critical is equal to 2.101. I've mentioned before that it's always good to draw the distribution with our critical values. So it's 2.101 is our t-crit. And then it's two-tailed, so we also are going to see that on the negative on the other end. Recall that if our data is in the tails, that's when we reject our null hypothesis. If it's in the tails, if it's in the middle, we do not reject our null hypothesis. Our calculated value of t is negative 1.510. That's our t statistic. And it's within that inner region. So we will retain the null hypothesis in this case. So, and we can look at this in terms of absolute values. So 1.510 is less than 2.101. Therefore, we retain our null hypothesis. Our p-value for finding this result would be greater than 0.05, and that suggests that there is not a significant difference in the mean score from the population of people who received education and those who did not. So this was based on option number 1, and we didn't find that there was a significant effect of this education, but maybe we could have designed this a little bit better. Maybe people in the groups had different levels of their baseline knowledge. This would be difficult to control and may contribute to our non-significant differences. So maybe there were some people in the no education group who had done a lot of work on their own prior to that, and we have no way to control for baseline knowledge. So there is another option for our question, and that's to do number 2, which would be a paired design followed by a paired sample t-test, and that will be covered in another mini lecture.